The last section in chapter 6 is about how to use a normal distribution to estimate or to approximate a binomial distribution. So we know the normal distribution is continuous. Remember? But the binomial distribution is the discrete distribution. But in this chapter, we're going to use a continuous distribution, a normal distribution, to approximate the discrete distribution, binomial distribution. Why we should do this? Because sometimes it's not easy to get the probability of the binomial distribution because long time ago we do not have computer. So each time we want to get the binomial probability, we're going to use the formula, but sometimes it's not easy to using the formula. So if we can use the normal distribution to estimate the binomial distribution, then we can use the table to help us to get the probability too. So let's check this together. So we just review the binomial distribution together. So we know what is the lowercase p. That's the probability of single success. And we also need to know the probability of failing. It's the lowercase q. And we know the relationship between p and q is p plus q is equal to 1. So we know p, we can get q. We know q, we can get p. And we also need to know the requirement for binomial distribution is both in p and q should be greater than or equal to 5. So this is also the requirement here. And we also know the special formula for the binomial distribution to get to the parameter like mu, sigma. We have the special formula, right? NP square root of NQ. This is just a quick review of binomial distribution. But because we're going to use the continuous distribution, normal distribution, to estimate the discrete distribution binomial. So we need to do some correction. We call it continuity correction. So we need to convert a single x value to an interval by minus half to plus half. So x value here is not a single x value. X value in binomial will be an interval in the normal distribution. This is called a continuity correction. Again, a single x value in the binomial distribution will be converted to an interval x minus 0.5 to x plus 0.5 in the normal distribution. So again, we just check what is the binomial distribution. Remember, we should fix number trials. So the trials number is not a variable, it's a fixed number. And all the trials should be independent to each other. These are the requirements for binomial distribution. And this is binomial, so we only have two kinds of possible categories for the results. Success, failure. Success, failure, two kinds of results, right? But success is not necessary to be good. Failure is not necessary to be bad thing. And the probability for single success remains the same. So P, which means p-value remains the same for each trial. And all the notations just the same notation in binomial distribution. So remember, don't forget what is p and what is q. So this is tell you why we could use the normal distribution to approximate the binomial distribution, because this is how we check the histogram, we realize, you see the curve? It's followed approximately a bell-shaped curve, right? Approximately, this is a bell-shaped curve, so suggests that we could use a normal distribution. We could use normal distribution. Of course, we need to check the requirements. So first, we should make sure the distribution is a binomial distribution. If it's not a binomial distribution, we cannot use the normal to approximate it, right? So we should guarantee the distribution is the binomial distribution. So we need to check the requirements to see if it is or not. So this is all the requirements for the binomial distribution. We can quickly go through it. After that, we know if it is a binomial distribution, then we have this two special formula to get the parameters mu and sigma. So we can get the value of these two parameters, mu and the sigma, by using the special formula. But don't forget, because we're going to use normal distribution. So normal distribution is continuous distribution to approximate a discrete distribution, binomial distribution. So don't forget the correction. We convert the single x value in binomial distribution to an interval in normal distribution by using minus and plus 0.5. Okay, so we quickly generalize all the procedure. So first, check the requirements for binomial distribution. Then use binomial distribution formula to get the parameter, if it is a binomial distribution. If it's not, then we just stop there, right? If it is a binomial distribution, then we use the special formulas for binomial distribution to get mu and sigma. So next step, don't forget to convert your single x value to an interval by using the continuity correction. So maybe the last step is try to still sketch a graph to help you understand. Let's check the example. So we have this famous experiment, and we know amount 580, offspring piece 145, or 25%. How can we get 25? We use 145 divided by 580 to get this 25, okay? Will be yellow. But he actually got 152, not 145. We assume the assumption is correct. 25 is correct. We assume that 1 is correct. We want to get the probability. To see the probability is very small or very large, then we can determine if this assumption is correct or not, right? So we need to find the probability getting 152 or more. So here it's greater than 152, right? So it's the single x value greater than 152. So if it's talking about the greater than, so we are interested in the area cumulative to the right side. And that is, we need to find the probability of this 152 greater than 152, greater than or equal to at least, which means we need to test 152 is a significantly high value or low value. Remember, if the probability of x greater than or equal to 152 is very small, less than or equal to 0.05, then we think this 152 is significantly high. If it's not the probability is higher than 0.05, then we think this 152 is not significant. Something like that. So that's the different form to interpret our answer. We can say we find the probability, then we use that probability to check if the assumption is correct or not, or we will say the value is significant or not. So first step, we quickly to check if the distribution is binomial distribution. So we know we only have two results. We know the NP, NQ greater than 5, and the result only can be sorted into two columns, green P, yellow P, right? We treat yellow as success. We treat yellow as success. So 25% of them are yellow P's. So we treat, then we use the binomial formula to get what is the mean and what is the mu, standard deviation. So first step, we check the distribution is binomial or not. If it's yes, then we can continue use the binomial formula to get the mu and the sigma. Step 3, we need to convert the single value to the interval by minus plus 0.5. So 152, we convert it to 151.5 and 152.5. Okay, single value of x will be converted to an interval plus minus 0.5. Step 4, we will try to draw the graph to help us understand. So we know we want to get 1.2 or more. But 1.2 or more, here 1.2 or more, so let me write down this. X is in binomial distribution. X should be the greater than 1, greater or equal to 1.0152. But after the continuity to normal distribution, we should switch the value to what? Single. If it's just x equal to 152, then we just transfer it to the interval 151.5 to 152.5. But this time, x is already not a single value. So we should get x is greater than a value after the continuity. But it's 151.5 or 152.5. Which one should we pick? It's minus 0.5 or plus 0.5. We need to test. How can we test which value we're going to pick? We just check the single value 152. Because here in the original binomial distribution, is single value 152 included in this interval? Is that possible to get 152? We will say yes. X greater than or equal to 152. So it's possible to get exactly 152. Let's check if we pick this as the value after the correction. X greater than 152.5. Is that correct? Is that possible to get 152? No. We will say no. It's greater than 152.5. So 152 is excluded. So this one is not a correct one. But we check the next one. 151.5. X is greater than 151.5. is this interval include 152? We will say yes. 152 is also included in this interval, so this one is the correct number we should use after the continuity. So we have two choices, right? Minus 0.5 or plus 0.5. But we should test which one is the value we're going to use. So after we test it, we know 151.5 is the value we're going to use. You can also check the graph to help you understand it because it's greater than. So he shaded this part to help you understand. You can also use my way to test the single value. The single value is included in the original data. Then the single value should be also included in the normal distribution. If the single value is not included in the binomial, then we should also exclude that single point in our normal distribution. Okay, next step, we should transfer our x value to the z-score. After that, we could. So don't mess up with last section. Last section, sometimes we talk about single x value. Sometimes we're talking about the mean value, x bar. But in this section, we only have x value. We're talking about the binomial distribution to normal distribution. We always talking about the single x value. So it's just the original z-score. So after the correction, we got this value. This is our new x value. This value will be the new x value in our normal distribution. Okay, so we just use this as our new x. So this is our new x. We already talked about why we pick this value, right? Why we could not just pick 152 because that one is without the correction. But which value should we use? 152.5 or 151.5? We already talked about the reason, so we know this time. Make sure 152 is included in the interval, so we need to pick this one. And we also realize we are talking about the area cumulative to the right, so make sure don't forget some step, okay? After we get the z-score, this is the z-score. So we use this z-score to check the area. So we check first two digits from the left column and the last digit top row. Then we can locate the area, 0.7325. But we know we cannot skip the last step. We cannot skip the last step because this is left side. And we are talking about any value at least or greater than this one. So we use the total area. Total area, 1 minus the area to the left to get the area to the right. So the 0.2676 is our final answer. Then we check the interpolation. So this value is from the type knowledge. So if we use the table, we will get to 2676. We see because this probability is not less than or equal to 0.05. So we can conclude this 152 is not significantly high. Right? So we cannot say the assumption is not correct. So the experimental does not contradict the theory. We cannot say the theory is incorrect because we do not get a very small probability. Only the probability is very small, less than 5%. Then we can say the assumption is not correct. Or we will say this value is a significantly high value. So that's the interpretation. Okay, we check the continuity correction again. Remember, if we have the single value x in the binomial distribution, we should convert it to the x minus 0.5 to x plus 0.5. Sometimes we do not have the single value in our binomial distribution, but we still need to do the correction. So we use this table to do the correction. So if in the binomial distribution, so this is this great value, so this is in binomial. And this is normal distribution, continuous. Binomial distribution. So okay, this is just binomial. This is normal distribution. So if it's at least 152, so includes 152 in the above. So we should pick 151 to make sure 152 is included, right? So includes 152 in binomial. Also need to make sure includes 152 in normal. But if it's more than 152, we check the single point 152, more than, so it doesn't include. It's not possible to get a 152. Any value greater than it, but never equal to, so does not include 152. Then we should pick 152.5 to make sure 151.5 152 is excluded. So for example, we say the single value here, x is greater than 152, right? Then we should, after the continuity, we have two values. 152. Which value should we pick for this case? We check the single point 152. We know there is no equal sign, so it's not possible to get exactly 152. If we pick this one, 151.5 greater than 151.5, then it's still possible to get 152, right? So this one is not the correct one. But if we pick this one, then we make sure 152 is excluded in this interval. So this one is the correct answer. So basically, we need to check the single point. Then we should pick which one is the correct value after the correction. So you can use my way to help you understand which value we pick, or you can memorize this table. Okay, you can memorize the correction table for the binomial distribution. Okay, let's see this one. Let's see this example. The same background for this example, but this time we want to find the probability of exactly 152 among 580. So we know n is 580. P is still 0.5, but we want to find this one. And we want to ask the question, is the result, is that probability, can help us determine if this 152 is significantly high or significantly low. First, let's check the probability. How can we get the probability? So this time we want to get the probability of a single value. P is equal to x equal to 152, right? So this time in the binomial distribution, it's just a single value. So if it's a single value in the normal distribution, we should convert it to the interval. convert it into the interval. I will write it here. It's greater than 151.5 to 152.5. So the single value converted to an interval. Then we need to convert this first value of x to the z. Convert the second value of the x to another z. Then each z-score we will find the area. This z-score for x we will find another area. Then find the difference. We can get the area of shaded part. So first we convert the first value of x, 155, to the z. First, convert the different x values to the different z-score. Next step, again, do not get the difference between two z-scores. Okay, we should use the z to find the corresponding area. So first, use z to get the area. Last step, find the difference between two areas. This is not the difference between z. We use z to get a different area. We get the difference of two areas. Then that one will be the shaded part, will be the area of a shaded part. So we know the probability is 0.0318. From the previous step, we get this probability. So we have finished the first part, right? 0.0. So the probability here, Px equals 152. So exactly 152. So that will be equal. Is equal to 0.0318. Oh, then we check the second question. Is this result useful for determining whether 152 a significantly high value or not? Some students will say, yes, it is, because this one is less than or equal to 0.05. So our conclusion is, yes, 152 is a significantly value. What do you think? Is that correct? Is that correct? If it's correct, then we get another conclusion, different conclusion from previous part. I will say this is not the correct one. Because when we can say a value is a significantly, when we can say 152 is significantly high, only if the probability of x greater than or equal to 152, this probability is less than 0.05. We check the difference here. Is that the probability of a single point, single x value? The probability is x equal to a value, and any value even higher than it, it's an interval. But in this case, we only count the probability of a single point, a single value. So this is not the correct probability to help us determine the value is significantly high or not. So we already know this one is very low. So from the technology, we will get this. But from the table, we will get this. Is not the relevant probability. The relevant probability should be this one. So in the previous example, we got the probability x equals 152 or more. That probability is the relevant, and this probability is not less than or equal to 0.05. So we can say 152 is not significant, or we will say the assumption is correct. We cannot say the assumption is not correct. So most of the time, we could use the technology to get the probability for binomial distribution. So make sure you understand we do not pick this one, the single value. We should pick the probability x or greater. So that's the relevant probability to determine this x value is significantly high or not. Similarly, when we want to talk about a single value is significantly low or not, we cannot use the single probability. We should use this one, this column, the probability of x, or even smaller than that value. The probability is less than 0.05. Then we can say that value is significantly low. Okay, always use this kind of value to determine the significance, not the single probability, single x values probability. So that's all for chapter 6.